Here we are. You did a wave refraction mini experiment activity, actually 3 activities. If you haven't yet done this, go back to them. So let's talk about a few of these here. You did a penny and mug experiment, and we had a certain set of conditions there. And there are some results from this that are going to really help you understand what refraction means and what it looks like. And so we're not going to go through each of the questions here, but hopefully you noticed that you set yourself so you couldn't see the penny, poured in the water, and then as that water level rose, you were able to see more and more of the penny until you could see the entire thing. And hopefully it should have been a pretty cool experience. But basically there are a few notes, there are conclusions that should have come from this, and maybe you have a hard time wording them, so I'm going to help you. Now, part of your assignment today is actually to write these notes down. You haven't written very much in the way of notes. You're going to write a few notes. You're going to write 5 total notes about what we're talking about here. So you're going to actually have on your piece of paper refraction notes. You can put today's date, and you'll write there note 1, 2, 3, 4, and 5. Don't write them all in yet. You don't know how much space they're going to take. So let's go. First thing, note 1. A simple conclusion from the penny and mug. Here's the note. So note 1. Adding water to a mug lets you see around the mug's edge. One more time, note 1. Adding water to a mug lets you see around the mug's edge. Hopefully you experienced that. So hopefully now you could take those words and combine them with that picture. You may have used different words yourself. You can actually adjust the wording slightly if it suits you better. But you should have that general way to phrase what happened when you added water to that mug. Interesting question here, a little bonus question. Why don't we normally notice this? I mean, you add water to mugs all the time. So you add coffee to mugs or tea to mugs. You add liquids to mugs all the time. Why don't you typically notice this? Okay. We next did the straw. And of course you had a certain setup for the straw. And what you should have noticed with that straw is if you looked just within the water, you didn't see anything special. Just within the air, you didn't see anything special. Well, you looked at both at the same time, and the straw didn't line up. So here is note 2. Note 2. A straw that is half in water looks like it is separated into 2 pieces. A straw that is half in water looks like it is separated into 2 pieces. All right. Now you've seen other examples like this, and you probably haven't quite noticed them. If anyone in your house wears glasses, pay attention when they're wearing them next time to the edges of their faces as you talk to them. A lot of things that are there that you just tend to not notice. All right, situation 3, you were to set a fire somewhere, on the stove hopefully, on the grill some people did, or you could use a lighter or matches, but the bigger flame from a stove or a grill is better. The grill, unfortunately, you have to wait till it really heats up. But anyway, what you should have noticed is similar to what you may have noticed when you've looked above a hot radiator, sometimes in school, if you get down on eye level with just the top of the radiator, or even a dashboard, I had mentioned this. You got a hot object, and then you look through the heat, so to speak. The heat itself doesn't have any sort of visual, but through the heat at some background object, you look like it was wobbling. So note 3. Note 3. Background objects look wobbly above a lit fire. Background objects look wobbly above a lit fire. You may have even noticed this on a baseball or a turf field. You get down low, sometimes on a real hot day, or above a track, above a road on a real sunny day, you might actually see this effect. But we literally saw it with a fire, so that's what we wrote here. All right, note 4 is a separate note. So that about covers everything we did here. I asked you if there's any real-life scenarios that matched any of these, and I just gave you a couple examples there. But note 4, Light usually travels in straight lines. Note 4. Light usually travels in straight lines. You may not have thought about this, but it's very intuitive in that when you look at something, we did a lesson on reflection. When you look at something, it's because for most things we look at, light is bouncing off of them and then traveling to your eye. And so if you want to reach out for a cup, you see where it is and you reach straight for it. You don't reach off to the side somehow or you follow a curvy path. If you see your fork or you want to eat, you see where the food is, you bring it straight to your mouth. So light usually travels in straight lines. And so now for the fifth note, which is really starting to tap into this whole refraction thing. The fifth note will really sort of rectify or connect note 4 with the previous three, because 4 says straight lines, and the previous three, we have these senses of bending or wobbly. So here's note 5. Adding water and heating air changes the direction that light travels. Notice this is not a very fancy explanation, but it fits what we did, and that's what makes it a good explanation. So note 5, adding water and heating air changes the direction that light travels. Great. So those are the 5 notes. You should have them written on a piece of paper. Take a picture, upload to Classroom, and on this basis will be the next lesson, which is part of today, Refraction 2. So we'll start to look at situations that are a little more complicated and a little less contrived, meaning they actually happen in regular life for certain people in certain situations. So again, get these notes down, take a picture, upload them, and then you'll go on to the next step, which involves watching a couple of videos and